Can't see anybody in the waiting room, and we certainly can't look through the glass door to see anybody standing in the hallway. So we will proceed. So welcome to all. I will share my screen and introduce you to the wonderful world of oleology with the MySelex technologies from the US and the work that we've been doing over the last few years. I'm Paul Callaghan, Director at Oleology. I've been working with MySelex technologies for the past 20 years. And today, this evening or this morning, we'll look at a few of the key items that are facing us at the moment, which is PFAS, the water filtering and polishing of which we've been able to do, but also the importance of the oil in water filtering and polishing and the ability to do both of those in a robust way. We'll talk a bit about the 3 dot points which follow: the MySelex and the technology to treat water, some technology comparison to put things into perspective, and we'll use the OLEOLOGY PFAS onion as a method of analogy. We've got some more people in the lobby, so we might just hold their view. Just one? Okay. We're in? Okay, so we have not missed much. We're just doing the introduction to what we will talk about tonight, which is the PFAS water polishing. And the ability of robust treatment for those other contaminants which are often in the water as well, principally being oil or organics in nature. So please do ask questions, or otherwise keep the mute on. We have some more people coming in. We're everybody in now? So if you can keep the mute on, if there is something that's of topical importance, then please bring it up. I'm happy to be interrupted to address things that are of particular interest to the participants in the webinar. So what we are about is one robust system to achieve the many compliances. MySelex as a technology removes hydrocarbons. We can recover oil droplets. We can separate oily solids and emulsions, and we can filter to parts per billion. That becomes particularly important to be able to do it in a small footprint with low operating costs, and particularly the third one, the minimal dry waste component, which is a key asset of the MySelex technology. To be environmentally safe and leave no residual chemicals in the water as a future liability are also very important components in achieving what we set out to do, which is demonstrated by those photos of removal of hydrocarbons in either BTEX soluble type products in water or highly emulsified and stable emulsions, using, in the right-hand photo, an infused cartridge. So we'll talk a little bit more about those particular aspects of MySelex technology in a minute. But just to wrap up on what else MySelex will remove, we'll also take out organometals, PFAS, which is the primary discussion tonight, and mercury. MySelex technology is particularly clever. It's a permanent infused fixed chemistry. Brings about 2 key operating parameters, and that's an oil absorbent, which is able to hold multiple times its own weight. And it's also hydrophobic. 2 very important elements when we get to talking about the waste and the importance of how to treat the waste, particularly when it's impacted with PFAS. MySelex technology comes in a range of filters, decreasing filter pore size, increasing contact between the MySelex, which is infused into the filters, and the contaminant which is targeted in the water stream. So as basically at a molecular level, contact between the contaminant in the water stream is improved with the lowering of the pore size, the tighter of the pore in the Miselex cartridge filter. So Miselex technology, and these are the key elements. It's a non-leaching, non-toxic, permanently infused fixed chemistry, which has great affinity for oils and organics as an absorbent, and it's hydrophobic in its various forms and its various stages. And there's principally 3 stages that we will talk about tonight. In the first stage, the Miselex can capture and separate oil from water down to a 5 micron oil droplet size. We can polish water, removing dispersed, emulsified and soluble organics from water, and that includes some PFAS. And then we can polish soluble contaminants in the final stage, highly soluble elements such as PFAS from water. The technology comparison, using droplet size as a way of demonstrating the various stages of removal by Miselex. The first stage, the Miselex Advanced Coalescer, removing oil droplets down to about 5 microns. And you can see the comparison going from left to right, left-hand side being larger oil droplets down to the right-hand side, smaller oil droplets, and the limitations of various conventional technology. So we want people to understand where the Miselex fits into the process. So when we come to looking at oil in water or PFAS in water, and the combination of both of those, which generally does occur when dealing with groundwater around fire training grounds, there are various limitations for conventional technologies, and there's limitations for the stages of Miselex technology as well. So the first stage technology down to about 5 microns oil droplet size. The second stage in removal of oil droplets closer to 2 microns in size, but more in the oily emulsion and oily soluble, oil emulsion and oily solid stages. The third stage, which is the Miselex polishing filters, the removal there is down to less than 1 micron in oil droplet size. So we're getting into the semi-soluble area. Below that for the polishing is where we deal with the PFAS, and we will concentrate on that somewhat tonight as the focus of what we really are interested in. So let's talk about a little bit of PFAS background. As you know, it's not found in nature. It's a synthetic organic made by man. Been around for the best part of 70 or 80 years. It's an organic, so Miselex has great affinity with it. It's linked to lots of cancers, liver, kidney, testicular, ovarian. Importantly, it's an endocrine disruptor. That's got a big impact on the environment, and in many countries around the world where the populations are around the coastline mostly, water treatment plants, sewer effluent, etc., ends up going into the ocean. So across the ocean now, the levels are measured between 5 and 20 picograms throughout the oceans. And when you consider 96% of the world's surface is water, that is a lot of PFAS, which is in our water system. We get to absorb it by ingestion and possibly by skin contact. The fact that it is so prevalent in our environment now, our generations and probably the 4 or 5 that follow us will be living with this forever chemical, given its half-life of 40 to 90 years at elevated levels for a period to come. Our clients, wherever they've been required to test for PFAS, have found it in their water. We've worked with the oil and gas, mining, leachate, landfill, industrial waste. It is literally everywhere. and that probably doesn't come as a shock to anybody listening into this. What is happening though now, as you would well be aware, the Stockholm Convention and the signatories to that around the world is leading to more adherence to reductions as more of the PFAS compounds are added to that convention list. Europe, as we know, is moving towards, in the next 5 to 10 years, want to ban a number of those PFAS compounds completely, so eradicate them from applications in Europe. The US is legislating by the mid of next year in 6 states for discharge criteria. Australia has gone through a round of revision for the National Environmental Management Plan, in which PFAS compounds have been added to that, which has driven the some of the work we've done here in Western Australia in recent times with a variety of industries, where the requirement for discharge into the environment has been less than detectable levels at super ultra trace. So that is, any level of detection prevented discharge of water, and the volumes of water have ranged from 400 million litres, what's that, 100 million gallons held in reservoirs, to millions of litres in various locations around the state, both inland and coastal. So the gathering storm is gathering momentum. We've been working in this area since about 2004. We've done a lot of work for Air Services, the government utility that provides fire training services, firefighting services, aviation rescue for all of the gazetted airports throughout Australia. They also provide services and training for some offshore countries as well, with limited fire training facilities. Our work has been vetted by Becker Environmental Services, and that work was done on behalf of their services for reporting into Parliament, federal government here in Australia. We've now put systems in industrial locations, in defence, and we've done some work for the oil and gas industry as well. PFAS, it's a growing concern. You can see the ranges there. 2,100 compounds up to 4,500 compounds late last year. It's now being discussed that they're in excess of 6,000 compounds that make up the PFAS group. The important thing about all of that is the range of products that it can be analysed for, or the range of compounds under that large umbrella of 6,000 odd that can actually be commercially tested for, analysed, is about 32 at most at the present stage, and that number's a recent number for discussions we're having with laboratories in the US, the same laboratory groups that we work with here in Australia. So you want to pick a technology that's able to remove everything, not just some targeted compounds, and that's something we'll talk about shortly. So, and the reason for that is the breakdown of precursors through a couple of different stages in their oxidizable life, back to their lower forms of compounds such as PFOA, which are regulated at the present stage as on the list of items that do have health impacts, like PFOS and PFHXS. PFOA lists highly on those compounds that you don't want reappearing later because you haven't been able to remove the full suite. We said that they're found everywhere, and everybody's familiar with AFFF firefighting foam, the metal plating industries, printed circuit boards. They're found as active ingredients in pesticides, waterproofing, clothing, carpets. and the reason that they end up in so many leachate areas, leachate groundwater from waste dumps, is as a result of many of those compounds being found in everyday applications. Just paper and grease-proof papers that are used in pizza boxes and cardboard cartons. A lot of high temp applications for oils and areas where oxidation resistance is required also have PFAS additives in there. Brake fluids are a good example of that. Aviation fluids are also further examples of those types of use of PFAS. Sealants and gaskets. The interesting facet of all of this is many wastewater treatment plants have need for treatment as they're discharging in many instances in inland locations into ground or into river systems. As a result of that, you need something with a relatively small footprint because the wastewater treatment plants, or in fact the potable water treatment plants, treatment of water for reuse, are landlocked and have limited areas of access. In our discussions with the US EPA a couple of months ago, we had follow-up questions from them with regards to size of plant that would be required to treat 110 million gallons of water per day to make it suitable for potable water. So the potable water treatment plant was existing, but the potable water treatment plant didn't have capacity for removal of PFAS. So we're able to assist them with indicative sizes for that, which was a fairly tight footprint for that volume of water, about 15 metres by 75 metres. Similarly with landfill leachate, we've done quite a bit of work in that area now. That's a growing concern because it's a continuous discharge, particularly from unlined landfill areas. PFAS is in all the oceans. So one of the greatest issues that we have in dealing with our clients and even some of our larger wastewater treatment companies is getting their head wrapped around the idea that whilst dealing with oil, they were required to treat to parts per million, but in the PFAS world, they're treating to points of parts per trillion. In Australia, we're looking at treatment of levels of recording down to 0.3 parts per trillion. And that's been the challenge for a few of those clients that I mentioned earlier, which had to treat to below detectable levels for the sum of all PFAS, not just PFOS or PFOA, but the total. And we're able to do that. And similarly in the US and the 6 states that we know of that are bringing in compliance regulation next year, they're all dealing in low parts per trillion as well. We're running through to intermission time, so if there's any questions that anybody has, we're happy to take them on the initial part now, or we can further plough on into more of the discussion. Okay, we will continue. It'd be easier if it was just PFAS and water only.
Sorry, I was just challenged to turn off my stinking mute button. Really interesting, and I really just interrupted because I want to apologize for having to drop off for a meeting at the top of the hour. But I was curious if the MySelects, it's kind of ironic, the spelling with this question, are able to catch PFAS micelles, which are not captured by absorptive media, but we have used some novel media at the end of a treatment train to catch the micelles that are weaving their way through the absorptive media. Have you looked at that?
Not in particular. That's something that we can come back to you on with that. So
Okay. Thank you.
Yeah. And what type of treatment were you were you referring to that you have been using?
Well, this was a treatment train put together, conceived of and put together to treat high concentration PFAS, for like fire training water waste or wastewater. And it's a multi-stage process with filtration up front and organoclaves and granular activated carbon and ion exchange, and we still come out at the end with PFAS, and we learned that was because the micelles were weaving their way through it. But in the novel media works, I can't be particularly specific about what it contains, but it's really expensive and it exhausts very quickly. So I'm wondering about a polishing step using a filtration technology would work.
Yes. Okay. So
Yes.
on that, I can talk about as we had an inquiry from a very large wastewater treatment company here. They have 125 installations around Australia. They contract wastewater removalists and treaters of waste in large volumes. They had similarly put in a system which contained a range of water treatment as a primary system, followed by carbon, and then ion exchange in a number of vessels. And as you described, they also had quick breakthrough. They were failing because they didn't have the robustness of the treatment train up in the front end, I guess, which is what we have done. So in this next section, which we're going to flow into right now, and I guess you're unfortunately about to leave us. We do. So we are able to remove, and the work that we've done takes high levels down to non-detect across the board. And we do that and utilize TOPA testing to ensure that we're not missing anything that as yet we're unable to analyze for as a specific compound. So across the board, we can be assured of removal of the total of those compounds. But I'll pick up some more information and perhaps get back to you on that separately.
Yeah, thanks for the presentation. This is Dave Woodward. One of the things that we are starting to kind of teach and sort of recognize, and it's not rocket science, but it's important because we always get the client question, quote unquote, what's the best way to treat PFAS? Well, when you look at our world of PFAS, we go from sort of leachate probably, which is really an industrial waste application with very high concentrations of lots of other stuff, right?
Yeah.
To maybe what Nate was just referring to is we have some DOD work where we're treating what you would consider, industrial fire water, thousands of ppm of TPH, and, up to 10 ppm, I think, of PFAS.
Yep.
Maybe a fire training area, which could be equally complex, where you have, glycols and chlorinated solvents and high petroleum hydrocarbons and biomass and, and then gravitating towards the easier applications which frankly, most of them have been to date more of a containment, a down gradient containment approach where, you might have, 100 ppt of total PFAS and you need to get that below 10 or something, It's really kind of just the polishing step only with no pre-treatment.
Yes.
So the reason I tell you that is, I think I know the answer, but with your technology, I think the key would be coupling that with whatever pre-treatment is necessary or to get to a point where you only have PFAS remaining. Is that right?
That is, yeah, I think you've read through the entire presentation to get to that point. Yes, that's exactly it. And as you're speaking, I'm actually thinking of, we did a job for a defence location here. It's off their fire training ground. We're taking the water directly off there. So we have varying levels of hydrocarbon as a fuel source. We have varying levels of fire training foam. But they didn't tell us that there was a third pipe underground that was coming in and fed water in from another source, which had 400,000 count of HPC in the water, which added exactly what you were talking about. So we have these enormous fluctuations between biologicals, hydrocarbons, and also PFAS in the water. So let me run through a couple of things here, because I think we're on the track now, which hopefully I can answer some of those questions for you. And keep in mind this part of the conversation we're having right now. So what I've got here is we don't have just PFAS in water, which is exactly what we're talking about. What we generally have is PFAS, hydrocarbons, organics, BTEX, solvents, algal blooms, you name it, it's laced in there. And you need an effective treatment for that range and mix as required that no one's going to tell you about. And if you're in a contract, if you're in a wastewater treatment plant that's contracting in water to be treated, that's being picked up from any range of industrial application, from fire training through mechanical workshops, general industrial waste, everything comes in at a different time, and you have peaks and spikes which you need to be able to deal with. And interestingly, we've been approached by 4 of the major PFAS competitors, we'd call them, for our pre-treatment, because they all suffer with premature failure and don't have the robust treatment at the front end. So we tend to call this the OLEOLOGY PFAS onion. In order to get to what's targeted in the red center, which is the PFAS, that part of it which is highly soluble in water and has a greater affinity for water than any other state, and because of that, it will leach from soil. So it is generally surrounded by something else. As we've just been discussing, you don't just find it on its own. And the biggest point of failure for most systems is the emulsions and the stable emulsions that are formed by fire training foams or firefighting foams. They're very strong surfactants and they form very stable emulsions. So in order to be successful, you need to remove and strip away the free oil. And there's often, if we think of the fire training applications or even the contract waste applications, where an excess of oil will meet a surfactant, the high MBAS level water from another source, or just be that at the fire training ground. Those will come together and form a stable oily emulsion. I got a very good example of work that we've done previously with this, where we were challenged at a airport here in Australia to treat water from a fire training ground that was a very dark grey in colour. And it was a stable chemical emulsion that they couldn't break. It had been through cyclones, induced air cyclonic separation, and they put it into tankage, waiting for it to separate, and it just didn't happen. So we were called in, and it was in the very early days. So this is 16 years ago we did this work, and the requirement was to get the oil level down. So no one was talking about PFAS in 2004, But the requirement in that particular time was to remove the oil from the water so it could be discharged to the local creek. What we ended up doing was stripping away the oily emulsion, and what we found later is we're using exactly that same series of cartridge filters to remove the oily emulsions, the semi-solubles, and ultimately the PFAS, which was that which caused the chemically stable emulsion, from the water, and we were discharging clear water at 0.6 parts per billion. It was a relatively small system, but highly effective. And that's all really about what needs to be done in a sequential but robust manner in order to be able to remove the PFAS, but do it in a commercially viable way. Premature breakthrough, one of the companies that came to us was it was less than 10,000 gallons of water treatment, and they were having breakthrough through a number of carbon towers that preceded ion exchange, and they were getting breakthrough. They were not able, through DAFs and a host of conventional equipment, able to remove satisfactorily the oily emulsions, the hydrocarbons that were lingering there, which caused failure. And they battled for 2 years to try and overcome the problem before they came to us for a solution. So what we have really, if we begin on the upper and first line, with a water treatment plant, which is a staged sequence of Miselex filtration, which provides a robust treatment. And that does what the arrows down the bottom indicate. It increases the rate of removal. It decreases the size of the plant. It decreases the cost of operation, but also capital costs to install or hire, or those mobilization and demobilization costs that are associated with hiring. Importantly, and really importantly, it decreases the waste. And we'll talk a little bit more about the waste. And associated with all of that, so not only from the treatment side for the lowering of the risk for future liability by removing the full range of PFAS components, but also the HSE risks that's associated with dealing with the waste. We end up with a dry waste. One of the great attributes of Miselex is it's hydrophobic. When we withdraw the cartridge from the filter housing, it comes out with only a bit of surface tension water. The contaminants are bound to the Miselex cartridge. That cartridge can then be stored safely because it's a very small volume. One of our plants, which we have in a defenceless facility, has been in operation for just over a year. They've generated just under half a pallet of waste, and they've treated 2.5 times the volume of water that we anticipated that they would treat according to their initial specifications. And they've still got those waste cartridges at site, so they're able to hold them there until they get enough of them to ship them safely. And even the shipping and transportation is a lower risk. You know, in the event of a rollover of a truck, they've got a dry waste to collect. They can pick it up from the side of the road. It's not a regeneration with a methanol at site is required with some of the ion exchange, and it's certainly not a sludge that's generated as a result of carbon regeneration. So what does that look like when we talk about the oleology with the Miselex technologies? A containerized solution, such as we've shown here, is capable of treating about 200,000 gallons of water a day of varying levels of PFAS and of varying levels of hydrocarbon and organics within the water, and maintaining a discharge of less than detectable levels. It's got very low energy, uses one small centrifugal pump. They can be automated and remote monitoring for inferring the state of and condition of the plant. Small footprint for what it does, and I can show you a relative size in a minute compared to a conventional GAC or activated carbon facility. The dry waste is minimal, as I've already spoken about. And the total treatment, so the water quality, the waste generated, the safety that's associated with it, and the future liability as a result of having no other chemical added to the water, and removal of all compounds across the range is a significant leap forward. And so when we're looking at that, and this is pertinent to the question that Nate was asking, I think, before, was across the range of how performance occurs. So this is field work that we've taken and graphically presented on a logarithmic scale. So we're starting at around, what's that, about 1600 micrograms per litre. That's at about 1.6 milligrams a litre, which is from a fire training ground. The initial part of 94% of all of the PFAS and hydrocarbon, we've only shown the PFAS for simplicity and clarity's sake on this graph, is done in the first container housing. So most of that work is done by the cartridges in the first container, and then the final polishing for the low level of residual removal is achieved by the second container, the Mycelex Performer media. The combination of both of those elements and the ability to remove either high or low levels in that first container and precondition the water to only low levels, basically homogenizing the water such that when it enters the polishing filters only ever see a low level consistent PFAS and low levels of hydrocarbon, if any residual, would remain in the water, so that we get ultimately very long life out of the Performer polisher. So let's put that in perspective with something like granular activated carbon. Now, for this, and in looking at these two graphs, we did the same pre-treatment with the Mycelex cartridge filters that you saw in the previous graph. The previous graph is that which is at the bottom of the page. The upper graph shows the relative performance of granular activated carbon when operating with the same empty bed contact time. So using like for like, so the same empty bed contact time, same volume of media, the granular activated carbon cannot remove to the levels across the board that the Mycelex Performer does. Further to that, there was work that was done, and I referred to it earlier, that was done by Becker Environmental for air services here in Australia. They went through, and this is part of the presentation that's available on the internet, and Nick Marquez, who did all the work, has approved our use of this information, which is publicly available. But it clearly states that the activated carbon is not effective in removing some of the short chains and susceptible to blinding by other organics and or carbons, just as we've been talking about a few minutes ago. Likewise, with the ion exchange, they suffer similarly if they don't have a significant pre-treatment to prolong the life of the media, and they point out the issues of regeneration is not always possible at some sites. So there are some significant limitations. We put this little table together really to try and hit upon the key elements as comparison. So small footprint is not achievable by GAC or ion exchange, certainly is by MySelects, and relatively in a 1-to-1 ratio. MySelects is about will perform at about 20 times the volume for the same footprint. Hydrocarbon removal is part of the robust nature, and in fact, really where MySelects began and has had significant inroads and work achieved through the oil industry. PFAS, GAC has its limits when looking across the full range. Ion exchange, by targeting specific ion exchange vessels, you certainly can achieve that, but MySelects does it as a matter of course. We don't need to regenerate it because we have such a small volume of waste when compared to other conventional systems. And we don't end up being blinded by suspended solids or sludge, and we are a dry waste. Putting that into a simple figure as a courtesy from Google Earth, the tankage and pipework that you see before you is a PFAS plant using conventional GAC to treat 700 cubic meters of water per day. I guess that's a couple of 100,000 gallons of water per day. And this system is only able to treat 4 of the 32 commonly analysed or laboratory analysed PFAS analytes. So by comparison, if we were to put our plant in there, that would be represented by the 4 rectangles, red rectangles, which in fact represent 4 20-foot containers. And on top of just being a very small footprint, this system with the MySelects technology would remove the hydrocarbons, would remove the PFAS, and would take them all to below detectable levels. The one same robust system, very small footprint. The containerized solution, as we've looked at previously, one small pump will do that. A smaller deployment, and another interesting case for an oil and gas client where we could have deployed either a container, but they requested to have the equipment on skids. We had a very high level of algal growth in the sumps, which were containing the PFAS impacted water. This water had to be treated to below detectable levels at the super ultra trace. And we did it through that one system. The interesting part of this is not only were we able to remove the PFAS from the fire training water and the algal bloom that occurred, as well as some of the other organics that were held in that water, but at the conclusion of treating the PFAS water, there were 17 isotainers of slops water, which had high levels of hydrocarbon from the gas plant. The inquiry was made as to whether we could treat that same water, and they were quite apprehensive at the idea of putting it through a PFAS plant, and we said we can happily treat that water through the plant. After initial testing, they were given approval to discharge to the environment with the water through that. And this is we've done this a number of times now for different clients in treating water that has not been able to be treated by other technologies and other vendors for the oil industry. So a small plant like that can treat 150 cubic meters of water per day, and that would all sit within a 20-foot container. And if you look at the 20-foot container image, the isometric on the left-hand side of the screen, you'll notice the two media housings which hold the performer polishing. What we're able to do with that is initially flow into the first housing, say on the left-hand side, and then flow to the housing that sits somewhat behind that to the right. After testing, and when we tested, eventually we do manage to see some breakthrough in the first housing, we're then able to reverse the flow such that we're able to change the media in the first housing and renew that. We can flow through what was the second housing now in the first position, changing the lag to the lead, and flow into the second housing, continue the method by which we can test between the two housings and after the second housing. In that manner, we don't have to, we're not bound to be batch testing and have large tankage requirements. We can test in between those housings, knowing that we have plenty of capacity in a kind of belt and braces approach to water treatment, such that the clients are able to treat water with greater safety and assurity of treatment and meeting discharge compliance, and also commercially gaining the full value of treating the volume that can be put through those housings. So this is a little bit on that particular solution. So we're able to treat the PFAS and the oil to below detectable levels, which in this case was 0.2 parts per trillion. We generated about a pallet of waste through treating both the oily water and the PFAS, and we were treating PFAS contaminated water for about 2.5 months before the final treatment for the last week of oily water.
You keep saying your big advantage is smaller volume, and I get that, you know, you don't have to dewater that or anything, and there's no water weight to it. But what I don't understand, maybe I've missed, is let's say, you know, a typical small pump and treat system, 100 GPM, for you're operating it for a year.
Yeah.
How much GAC would you generate versus resin versus your product in terms of waste? And I would think that you keep mentioning ion exchange from a regeneration perspective, but I would think that your product really is competing more with the single-use resins. So maybe, you know, I'm trying to get a relative, you know, is it, you know, half the waste generated with carbon and a quarter of the waste generated with, you know, resin, just a relative feel for, because waste disposal is becoming more difficult and costly in the US very rapidly.
And we likewise are challenged with the same issue with waste here. Even more difficult to treat waste here in Australia because Department of Defence here has a mandate that they want all of the contaminated waste, PFAS contaminated waste, thermally oxidized. And there are only 2 plants in Australia that are licensed to treat PFAS via thermal oxidation. So exactly the same circumstances and need to treat. So the waste generation is about 5 to 10% of that of GAC. So it's significantly less. And
but you're disposing of that versus regenerating that.
Yes. But we're also removing all of the PFAS analytes, not just some, and removing them. So GAC has a very significant problem with short chain PFAS and getting to below detectable levels. They couldn't do it for the particular clients that we have now, and defence is one of the main clients that we now supply to. So there's two very important areas here. One is achieving the levels of compliance that are required, and the throughput and the footprint, which are all very positives for the MySelect's technology by comparison, because we're significantly smaller in the footprint. But as a result of that much smaller footprint, we also have much smaller waste and in total. So we are at a significant advantage in terms of the volume of waste generated. So to run a plant that we have in a defence site for just on a year, we've generated about half a pallet of a standard shipping pallet over the course of 1 year. Does that give the perspective that you were seeking in terms of relativity?
Yeah, well, you didn't mention, comparing that against the single-use resins. I mean, one of the advantages of the single-use resins is their capacity is much greater than the regenerable resins.
Yes, but again, we're in that point where single-use resins are fairly much targeted to a smaller group of PFAS compounds. So our clients have been looking for a complete removal across the board, which they haven't been able to achieve. And we're in conjunction with ion exchange in either groundwater applications or around fire training ground applications. There is a quick breakthrough. So the client that we were dealing with, which was changing out the resin after 10,000 gallons, we were looking at, and it literally was a failure of breakthrough. We were looking at so 10,000 gallons. So that was 4 hours of treatment. So we were looking at a change of media once a year. So it's a very significant shift in terms of volume of treatment of water and the compliant levels of discharge of that water for a very small volume of waste generated. Okay. That in principle is the system. So as shown on that graphic, waste from a variety of areas through, first of all, the primary stage of oil separation. If we have free and dispersed oils, no waste as a result of regeneration, only recovery of oil, and we have no consumable. In the second stage, the MXR with the regenerable media, again, no consumable. We get into the cartridge stage, and by this point now we've removed the emulsified oily solids, and we're down to the primary stages or the tertiary stages of separation for the hydrocarbons and the primary stages of removal for the PFAS through a multiple number of cartridge housings, and then into the performer for the final polish and discharge. I guess we can take some questions at this point. If there's anything further that I can help you with there. Otherwise, happy for questions to be answered via email. We can certainly send an information pack to you as well as a result of that for those who would like something further with some more detail.
Paul, this is Bonani Langan. I work with Sasha to organize this webinar. Would you be able to send the slides and the recording to share with anybody who couldn't attend this morning?
Certainly, Bonani, we can certainly do that. Sasha will organize that with you, and thank you for helping to get this together. We're pleased to be able to assist. Yeah,
we do appreciate your time. I know that many people are going to have to drop off pretty soon, but there was one question on a cost comparison between GAC and the MySelect technology. Do you have any kind of order of magnitude comparisons that you can share?
I guess look, it is significantly cheaper, but we're talking. It's not an apples for apples comparison again because of what we remove. So the total cost is certainly probably in the order, and by total cost I mean when we start talking about the waste which needs to be considered as well, and I'm just talking operational cost. Setup cost is significantly cheaper. The capital infrastructure is much less with the MySelects compared to a GAC setup, and the operating costs, we run at much lower pressure, so much lower in terms of energy consumption. The waste generation is much less, so we're about a 20th of the waste. So in orders of magnitude, somewhere between 20 to 40% less in cost would be a conservative relative measure for that question, Bonani.
Okay, thank you. There's just, maybe this will be our last question. There's one more question regarding what is the mechanism of the filtration?
The mechanism of the filtration is well, it's the MySelection fusion, so it's an adsorption via the patented MySelects molecule, which is permanently infused into various substrates. Principally, the cartridge filters are the area where the majority of the reduction does occur in the high levels of PFAS, and then that. Yeah, well, that's the mechanism.
Okay. Well, let's open it up. Did anybody have any other questions they had for Paul? No? Okay. Well, Paul and your team, thank you so much for your time. I know it took a little bit of time to get us on the schedule, so I do appreciate it. And we will definitely take your contact information and distribute it to our group. And as they have additional questions, I'll ask them to reach out to you individually.
Thank you, Bonani. Thank you, everybody. It's been a pleasure to present.
Yes, thank you again for your time.
Okay, goodbye for all.